Well, thank you for inviting me down here. I hope that what I'm going to present here will be of interest to you. It certainly is a great interest to the city of Hastings because we're facing some significant problems here dealing with nitrates and uranium. What I'd like to do is first just give you a brief overview of our system. We have a fairly simple water system. We have no water storage. We just pump directly into the distribution system with our wells. We have no treatment. We've enjoyed that luxury for approximately 130 years, and unfortunately, those days may be ending. We do supply water to the village of Trumbull because they had a nitrate problem. We extended a line out to them. There are a private water system, Hastings East Industrial Park and Central Community College on the east side of Hastings, and we also supply water to. And within the Hastings area, there's several communities that are being impacted by nitrates as well. It includes the villages of Juniata, Glenville, Inland, some school districts, and some rural subdivisions. Just generally here, the groundwater flows from the northwest to the southeast. City of Hastings is located right here, and so we see that we're influenced by the Platte River. This is a map showing the 20-year travel time that we have calculated for the municipal wells in the city of Hastings. And you can see many of our wells here in the northwestern part of the city, this being the city of Hastings. One thing to note is that there is a large feedlot that's just on the edge of that 20-year travel time. That feedlot does house about 45,000 head. This is the village of Juniata. So the groundwater modeling, we conducted that in 1995, and we've since updated it in 2009. And these are just some round numbers, but approximately 50% of the water that we get into our wells is recharged from the Platte River. Approximately 25% of that recharge comes from rainfall between the lands between the city of Hastings and the Platte River, and the other 25% roughly comes from irrigation return. What's important to take from that is that 50% of the water we receive flows through the root zone before we get it into the municipal wells here. The travel time between the Platte River and the city of Hastings is approximately 50 years. If you were just to look at the gradient that we have, you would see that it's much longer period of time than that. You know, using about a foot per day, foot to 2 foot per day water flow. But because of pumping, the rate at which water is coming in from the Platte River is increased considerably. So one way to look at it is that the water we're drinking today is the water that was in the Platte River in 1964, or about the time I was born. The Vado zone that we have varies from along the Platte River being very sandy to approximately 60 to 80 feet of clay, loess material that's near the city of Hastings. It's a little uncertain about how fast that water flows through the Vado zone, but we've estimated that it'll take about 50 years. There's some data that's been done at the Municipal Research Center that it may be even faster than that. But another way to look at that is that the water we're drinking today was the irrigation water and rainfall that occurred in 1964 in the Hastings area. So what are our issues? We're dealing with nitrates, uranium, gross alpha, selenium, pH, hardness, inorganic levels are all increasing. We're getting hit with a lot of things. We're detecting atrazine at low levels. We've taken several wells offline due to nitrates, and by 2016 we won't have enough water to meet our maximum day demand without doing some kind of blending or treatment. This is just a graph that we put together that monitors our capacities in our system. Basically, this is just an estimate of the wells that will be taken off, or the wells that are still remaining online and their capacities versus what we need for pumping. And you can see about 2016 we're going to hit a point where we won't have enough water. So our Hastings Utilities Board of Public Works gave us some marching orders. They said implement a wellhead protection plan. And in 1995 we had started that process, but there really wasn't a lot of interest because we still had good clean water, but the issue became more of a concern here in the last few years. They wanted us to enlist the help of the NRDs because we don't have jurisdiction outside the city of Hastings for those kinds of activities. We'd have to work with counties or NRDs, and the NRDs was the obvious choice to go to. And the Board of Public Works said, find a solution, think outside the box. And I think that's kind of why I'm here today, because we're thinking outside the box. So defining the problem, is the source of nitrogen a rural or urban problem? We had a lot of people tell us that it's the feedlot, it's the lawn and garden fertilization in town, etc. What we realized was there was insufficient data to actually define the nitrate problem, and we needed to do a lot of water sampling. In 2010, we collected 576 water samples over the 76 square miles of the wellhead protection area, which accounted for 87.5% of all the wells that were out there. We had some owners that just absolutely refused to give us permission to get water. In 2011, after looking at those results, our Board of Public Works asked us to extend that study area to 200 square miles, and we collected 42 samples for uranium. The combined results of the 2010-2011 water sampling showed that 25% of all the samples that we collected were in excess of the MCL of 10 milligrams per liter for nitrates, and uranium levels range from 1 to nearly 75 parts per billion, keeping in mind the MCL is 30 parts per billion. In 2012, we collected another 138 water samples, and we saw roughly 25% of those samples exceeded the nitrate levels. But more surprising to us, and part of the reason for doing the additional sampling was to really get a better handle on those uranium levels. We found one location was high as 345 parts per billion, in excess of 10 times the MCL. I just make a point at this point is that the farmers out there had no idea they were drinking that water. They don't test their wells for uranium, but with the municipality we do. So that was a very enlightening piece of data that we started sharing with the public out there in the rural area. In 2013, we collected another 58 water samples and saw no significant change to the data we'd already collected. Here in 2014, we'll collect at least a minimum of 40. That's part of our nitrate management plan. And then all of those wells will be resampled again in 2015, probably 2015, 2016. That's just a lot of wells to try to get done during the irrigation season. Here's a map that shows the nitrates that we've encountered. I'll just point out the red box that you see here is the 200 square mile area. The yellow line is the wellhead protection area. This blue line is the boundary between Upper Big Blue and the Little Blue NRD. We actually have to deal with both NRDs. The city of Hastings is sitting in here better nitrates. The brown area represents 8 milligrams per liter, and then the red and purple areas are higher levels of nitrates. And just point out that right in this area we found nitrates at 75 parts per million. And you can see there's quite a bit of nitrates coming in off the Platte River. Though the data is somewhat sparse because we don't have quite as many data points out there, we did go outside our 200 square mile area. I will just want to point out what's significant is that this area has high iron, and so we would have expected to see lower nitrates. This area down in here is a lot thicker aquifer, and we suspect that there are still a lot of nitrates down here, but just because the irrigation well takes a sample that's a composite of the entire depth of the aquifer, that we're probably not seeing those nitrates that are actually down here. We've got some a good profile of water. In addition to just looking at water sampling, we did vadostone sampling. We took samples from 19 sites. We went to approximately 100 feet, tried to get the groundwater where we could. We found on the average we're between 500 to 2,000 pounds of nitrogen is located per acre below the root zone. So at this point, we have a future contamination source. Keep in mind, 50% of that water that we get recharged in our wells is coming through that root zone, which means it's coming through this zone. We also did isotope sampling, and it showed pretty conclusively that the issue is anhydrous ammonia or commercial fertilizers. This is just a graph that shows that sampling results. Just want to point out one outlier out here. That turned out to be, there was an old farmstead. The lady had lived there all her life. It was an old dairy, and we suspect it was probably related to that dairy because all the samples around her, upgradient, downgradient, etc., all showed that it was commercial fertilizer. So nitrates can become from both the fertilizer and use of animal waste or those wastes that were left behind by that operation. So we generally try to tell the public that it doesn't matter whether you're urban or rural. Anytime you use fertilizers and you have excess irrigation, there's a potential of losing those nitrates into the aquifer. That if we do, and as we do nitrate management for the area, we recognize that water management is part of it. One of the things I found interesting in visiting with the farmers is that they knowingly put on at least 30% more fertilizer than they need because they know they lose it past the root zone. They're aware of that. They know that because of heavy rains, you get a rainy year. If they don't put that on, they don't have enough for their expected yield. And so we see that water conservation is equally important for managing those the nitrogen that you're putting on. So we're stressing water meters and water conservation practices along with making sure that you put on nitrogen at a spoon feed it or put it on at applicable rates, etc. The uranium sampling. We started the uranium sampling not because it was an issue of nitrates, but because we were dealing with an increased level of gross alpha in our municipal system. We just didn't understand why that was occurring. We were seeing some uranium starting to pick up in some of those municipal wells. And so it was just kind of our effort to say, well, let's kind of see what's out there. Unfortunately, we saw a lot more than what we hoped to see here. Keeping in mind that I pointed out that we had high nitrates up in this area, we're not very far from there. We see the highest levels of uranium at 300 parts per, or in excess of 300 parts per billion. The municipal wells are located right in here. Groundwater's flowing. We're just starting to skirt that edge of some major amounts of uranium. Since uranium was an unexpected problem, we started asking ourselves, where's this coming from? Is it naturally occurring? Is it from phosphate fertilizers? And we understood that phosphate fertilizers are made from a rock that has uranium fluoride in it and phosphorus in it. So we just curious whether that was being not regulated sufficiently. Especially when we saw there were high levels of nitrates, that maybe we were seeing high levels of phosphates being applied as well. And kind of caught wind that biological processes may be involved. So we started looking at those issues, and we asked ourselves a pretty simple question. We said, if it's naturally occurring, because we knew in the Grand Island area along the Platte River that they do have uranium that's been there, but we said, why is it now just showing up in our municipal wells? Why are we seeing a change? If it was naturally occurring, it should be somewhat stable, at least over the last 50 years or so. With the amount of irrigation we had has been somewhat stable. In fact, it's probably gone down a little bit. But we just looked at that question, said it just didn't make sense, and so we needed more information to give us a better handle for that. And I'm going to go through a couple more points here, but I'll come back to this issue of where we want to go with this uranium problem. So as far as the city of Hastings is concerned, how do we solve this problem? Do we go find an alternative aquifer? There really isn't one out there. And nitrate sampling shows it's probably everywhere. Conventional treatment is obviously an option, but we don't have a centralized treatment system, as I pointed out earlier. We need to do a lot in our system to get to the point where we can have maybe one point feeding into the system. We understood wellhead management can play a role, but it won't solve the problem. It's really the long-term problem. Our Wellhead Protection Committee basically said, we can't solve your short-term problem. Hastings Utilities, that's your problem. We'll work on the long-term issue. So what was our management plan objectives? We wanted to make sure we could get a plan in place where it could give us the next 50 years of water, reliable supply of water. We want to reduce the financial impact to our utility and the customers that use that water. We want to protect the viability of the aquifer. And just as importantly, is to make sure we try to maximize the use of our existing infrastructure. Because if we start replacing that, we're losing a lot of value in our system. We did a study to see what it would cost to treat water for the city of Hastings, and the takeaway here is that reverse osmosis, even though it is slightly more expensive at about $75 million, because of the issues of selenium, the atrazine. There was chrome issues that are out there. We felt that RO was probably the best choice to make. These annual costs are additive as we go through. Roughly what you see is over the next 20 years, we would have to spend $100 million for the city of Hastings. And we're a population of 25,000 people and roughly 10,000 service connections. So the out of the box thinking brought us to maybe a different plan here. We call it our well-based nitrate and uranium management approach, and we're looking at 5 items that we want to work on: dual pumping, aquifer storage and restoration, focused water treatment, irrigation management, and blending and storage. This dual pumping concept is something that we recognized early on in our investigation, that some wells were low in nitrates, but they were located next to maybe a irrigation well that was high in nitrates. And what we found out was it was a domestic well that didn't pump very much. It never created a cone of depression. And the newer the well was, the deeper that the well drillers in the area were drilling them. They had suspected that if they go deeper, they can find better water. So they already had an inkling that the nitrates were at the top of the aquifer. And what we found was, and we've got 2 dual pump projects going on now, but if you put in 2 pumps inside an existing well, pump them at the same time, the nitrates that are floating on top of the aquifer will tend to come into that higher pump versus that lower pump. And we're in essence able to separate those 2 water qualities apart, and in the 2 cases that we have, we were actually able to produce a potable water from that lower well, whereas the combined was actually above the MCL. Aquifer storage and restoration basically is to take the clean water, re-inject it in an area upgraded of our municipal wells, and basically store that water in the aquifer for future use by those wells. Basically, we use the aquifer as just a big storage tank anyway, and so this concept seemed pretty common to us, or appropriate, in that if we can put some clean water into that big storage tank, we can reduce by blending in the aquifer some of those nitrates, and then supply that water to the existing municipal wells. The big advantage here is that we can, well, let me go to the treatment. The big advantage of using the ASR process is that the treatment capacity only needs to be about 6,000 gallons a minute around the clock every day of the year, versus trying to meet our maximum day demand of almost 18,000 gallons a minute. So we can cut the treatment plant down by about a third. We can also then tailor that treatment with different treatment processes, and in the case of uranium, we use an absorption of media. The nitrate removal, we use reverse osmosis. There would be some residuals that would be generated because of that process. We would send some to our wastewater treatment plant. It only has a certain amount of capacity. The other part of it actually go to a lagoon and a storage system, where this is where the irrigation, reuse, and management comes into play. We're actually going to use this water, this high nitrate water, for irrigation. And we're going to supply it to the area that is being served today by irrigation wells in that area that we are going to be re-injecting. We don't want that farmer out there taking clean water out to irrigate with his fields. We're going to give him those high nitrate waters. And we're going to actually use that crop uptake to consume up some of those nitrates. Because one of the biggest problems we have is we don't have a big flowing stream. We can't get rid of these nitrates. We can't just dump them down the creek. But the best we can do is probably evaporate it with them. And in this case, we're going to try to use the agricultural production. So ag, put it there. We're going to use ag to try to help us clean it up. So it's kind of like using lemons to make lemonade. Obviously, we could do blending. Several of the municipal wells could be blended together. We can put in mains, tie them to a central point, and those wells that are low in nitrates, they would be blended with those wells that are higher in nitrates. So with that concept, as you can see here in this cost estimate, we're able to reduce about $30 million out of that $76 million cost estimate that we had originally proposed here. The O&M would go down roughly the same amount. However, for the city of Hastings, it brings some risk because we're combining various technologies. Though been proven at other locations, is really bringing them together as one program and see if they'll work together. We feel fairly comfortable it will. because at the very outside, if we cannot get the dual pumps to work efficiently or the ASR is not as efficient, we simply just build more treatment and overcome some of that. So we think that this is an approach that we need to take, but it's still a lot of money for the city of Hastings. So getting back to our uranium issues here, we just needed to better understand this. I mean, I had heard that we should not have uranium, we should not have selenium out there, but we did. And so kind of through the NRDs, I got a hold of Dr. Weber here and indicated that biological activity may be part of the answer that we were looking for. So as you saw earlier, I think she's on to something here. So trying to answer is uranium naturally occurring? And the answer is, well, uranium's definitely out there. It's in the soil, so we had it. Now what's causing it to move? I brought a lot of questions to Carrie, and there was a lot of things that was bouncing around in my head. And one of the things that we noticed was we knew we had uranium because we was doing gamma logging on all these wells, so we knew we had a radioactive source in those clays that were out there. We understand that nitrates and carbonates, iron, pH, all those things were contributing to the issue. We know that life in the groundwater is there. We've seen that in biofilms. We knew that from just being able to maintain our municipal wells. We have to do a lot of biological removal in the screen area. pH, in the last 15 years, we've seen a steady increase from 7.75 to 8.85. Keep in mind that the pH that we can deliver to the water system is 9. So we're even getting close to exceeding pH issues. We know that velocities have increased over the last 50 years, obviously due to increased irrigation. More pumping means that water's got to flow faster to us. We saw that in our modeling. We know that hardness is increasing. We know that CO2 is being released. Every time we have a well taken out of service and do cleaning, we see calcium carbonate build up, and we know that there's CO2 being released when that precipitates out. One of the things that we realized was that recycling of irrigation water, we suspect that the water the farmers are pumping, they may have pumped it a couple of times already, and that every time they pump it, no matter what kind of irrigation system you have, there's evaporation that's occurring. And so just like your coffee or my water glass that I let sit around for many days, it starts to get mineral salts in it. And what we know is that every time they pump this water out, we're losing some fresh water out to evaporation, and we're putting more mineral salts back into the soil. So what then became a concern to us was that the soils that we're seeing in the area are becoming more acidic, but yet our groundwater is becoming more alkaline, and we're putting more alkaline water out there. So something is definitely going on in the system. We understand that as we've added, excuse me, nitrates and phosphates to our system, that we're providing a food source. As I pointed out here, we see iron in this area. We see the red areas are nitrates, and sure enough, this uranium sits in that zone between the nitrates and the iron. So it looks like it's a happy hunting ground for the bacteria in that area. So the uranium saga continues. We hopefully to do more work with Dr. Carey, and I really appreciate all the assistance up to this point. She's kept me from getting insane, I think, at this point, trying to figure out all this. So with that, open it up to questions.
Questions from the audience?
For your dual pumping system that you were talking about for the city, what are the depths that those pumps are going to, and is there potential for that to be affordable for rural private wells as well, or is the economics of that way ahead of the population?
I didn't quite catch that, but let's see if I can, maybe I caught enough. But the cost of the dual pumps, we haven't really kept track of that because at this point it's really a pilot study. But you're really limited on the casing size. So a small domestic well, you're just not going to get much more than those small pumps. These are large industrial wells that we have. They're 18-inch, and some of the older wells actually have a 24-inch OD, and that's what we've been working on. But the advantage with the dual pump is that we can apply it to those larger wells, and then obviously it's something that when we look at the next new wells, we're looking at something like a 30 or 36-inch casing to try to get more pump in there. But I will just give you a clue. My next dual pump project is actually 3 pumps. We have a triplex system that we've got designed right now. We should be installing it this summer.
Two questions. First, is it correct that only about 5% of municipal water is actually consumed by people of the total supply?
You know, we've been asked that question, and to say how much is you drink might be one answer to that, but that's not the entire piece. We need to think about what are all of the water used for potable needs, like food preparation, the hospital, we got a bakery in town, we have meat packing in town, and I can tell you that during the summertime, the amount of water consumption goes up because of irrigation. And when we look at just the summer months compared to the winter months, we see about 30% more water is being used for the entire year. If you average that over the year, about 30% of our water is actually used for irrigation. The rest of that water is used for, you know, the car wash, for the potable needs of the community. But because of the type of industry we have in town, they do use quite a bit of water for potable needs. Okay.
Well, I guess what I was getting at, thanks for answering that question, as if you considered sort of 2 types of water supply, one potable for human consumption or, say, food-based water usage, and a non-potable supply.
Absolutely. And our first step is this irrigation system that's out there. And didn't show the drawing, but right next to the storage lagoon that we have planned, there is a city park. And there's also a city ball field that's right there. It's part of the Lake Hastings recreational area that's there. And we're planning on using that water for those areas. I wish I could go back 100 years ago and put in 2 water lines down every street and sidewalk in town. So there's an issue of trying to get those systems in there. But we think by doing this, we can get a jump start on that, and maybe get people more interested in it. So we'll try to use this in the parks as much as we can, and that's where the dual pumps come in, because many of the municipal wells we build them in city parks because that was city-owned property. Okay. So, very good question. If I was building in a new city today, it'd have 2 water lines.
Is there a difference in the uranium and nitrate concentrations with depth, such that when you're pumping, the dual pumping or 3-way pumping, will you be concentrating uranium the same way you'll be concentrating nitrates?
Yeah, absolutely. Now, the 2 dual pump projects that we have, we were limited in casing size and really what we could do. But the very first one we had a 12. Well, the well could actually pump 4,000 gallons a minute. We're operating at about 1,500 gallons a minute. We have a 60-gallon a minute pump that's just above the top of the screen. And what we see in that top layer, we see roughly 40% more uranium, nitrates, selenium, chrome. They're all in there. That's all at the top, which led us to believe that the problem isn't coming from the Platte River. It's coming from the soils at above, because there's really no mechanism to mix in the aquifers that comes in there. And the only thing that's in reverse of that is fluoride. Not really sure why. Maybe there's somebody that can explain that to me.
So is there any concern about using that that top layer for irrigation, given all the uranium in there?
Yeah, and actually what we've done is we've asked the question, how much uranium could we put out there? I'm not really getting a very good answer from the ag community, whatever. There's not a lot of research there. But we have decided, because of liability of putting this on somebody else's property, that we will treat it to the MCL for uranium. Because obviously if we're watering our lawns and gardens in town, that's the level. So we're going to go the extra mile and do that as well. But there is a lot of agricultural production out there, not only corn, soybeans, but the gardens out there, the livestock that's out there. there are areas out there in excess of the drinking water level. I don't know what that means.
Has there been any concern from the medical community, especially the dialysis units, if they are using water with high nitrate or high uranium?
Well, from the issue of nitrates, I mean, we're an ag community. There's been a lot of good information out there. People understand it fairly well. In fact, a lot of people say, well, it doesn't hurt me. Why am I worried about it? But obviously the infants and the newborn and so forth. But the issue I'm hearing now is the public saying, what about this uranium? There's a lot of cancer that's out there that I can't prove, whatever. The NRDs have coined a phrase, uranium may be the next four-letter word for water issues.
Yeah, and as part of a project last summer, we looked at the data from the state health department for all the municipalities along the Central Platte, and there was obviously some wells that had to be shut down, not just because of nitrate, but also because of uranium. Many of the communities in the Platte Valley and other places in Nebraska have had to add treatment or some other alternative for increasing uranium and nitrate. And it's not, as Kara pointed out in her presentation, it's not just Nebraska, it's the High Plains Aquifer, the Ogallala Aquifer, and other states. California is in particular is dealing with increasing uranium and nitrate in their groundwater impacted by agriculture. So this is a growing problem. Yeah. All right. Thank you very much.